Okay, let's work now on a problem from the textbook of Garrett and Grisham. It's problem number 3, and it appears in page 76. It's to calculate the delta G from the delta G naught prime. So let's get the information here in the work on the problem. The problem says the standard state free energy of hydrolysis for acetyl phosphate is delta G naught prime, delta G naught prime equals minus 42.3 kilojoules per mole, and it gives the reaction also, which is acetyl P react with what? It's a hydrolysis, right? Reacts with water, and they give then the acetate and plus Pi. So this is the information that is in the problem, and they ask to calculate the free energy change for acetyl phosphate hydrolysis in a solution with 2 millimolar of acetate. So acetate is going to be 2 millimolar, and the phosphate also is 2 millimolar. Phosphate also 2 millimolar, and the concentration of acetyl phosphate equals 3 nanomolar. Be careful here, okay? 3 nanomolar. This is a nanomolar. Okay? So let's work on this problem. It's a simple problem. Let's use the equation. Delta G equals delta G naught plus RT natural log of Q. Okay, so we know that R, the constant, is 8.314 in joules per mole, and temperature is in Kelvin, right? We don't know the temperature, he was not given in the problem, but when it's a situation like that, we assume that's room temperature, and the room temperature is assumed to be 25 Celsius. So in that case, the temperature for this problem would be 298 K. Another situation here that could have the students get confused is that we need delta G naught, and it was given to us delta G naught prime. So one is in the other biochemical conditions, right? This one in here, delta G naught prime, or delta G prime naught. However, this reaction has no protons, so the only thing that changes is the concentration of protons from one to the other. So you can use delta G naught prime as delta G naught in this particular case. So it simplifies the problem. So let's plug in everything that we have, delta G. And now it's better that we work with the units of joules, not kilojoules. So instead of having 42.3 kilojoules, let's write 42,300 joules for the delta G naught, which is the same as delta G naught prime in this case. Then we have R, that's 8.314. We have the temperature, which is 298. And now we have the natural log of Q. Q is the reaction quotient. It resembles the equilibrium constant, except that's not in equilibrium, right? What the equilibrium constant is? The concentration of the products that are acetate and phosphate, right? These two products, and here goes on the numerator. So what's the concentration of acetate? Acetate is 2 millimolar, and phosphate is 2 millimolar. So let's write the two, because we have to multiply one by the other. So let's write 2, 10 to the power of negative 3 squared, okay? Same thing, right? And divide by the concentration of the starting material, which is, in that case, acetyl P. And the concentration of acetyl P is 3, 10 to the power of negative 9, because it's nanomolar. right? And then why do I put water? Because water is a constant. Water is not changing, so water is not part of the equation here. So let's use the calculator. Scroll up a little bit here so that we have a little bit more room to write. And let's use the calculator. First of all, this term here is going to be 4/3 of 10 to the power of 3. This is just for this part. All right, so that we take the logarithm of that, it's going to give 7.19. That's again natural logarithm, and multiply that by 298. I'm using the calculator. You can use the calculator there as well, and multiply by 83.14. All right, so let's repeat here. Delta G equals minus 42,300, and this whole thing here gave 17,827. Okay, now we sum up. That's going to be delta G negative 24,472, and this was in joules per mole, right? We don't want to write like that, so it's better to write approximately minus 24.5 kilojoules per mole, which is the solution for this problem 3 of chapter 3 from Garrett and Grisham.